Today we are going to be starting the last section that I'm going to cover on sequences, and that is 9.3, geometric sequences. So whereas an arithmetic sequence is a sequence with a common difference, so we're adding or subtracting to go from one term to the next, a geometric sequence is a sequence with a constant ratio. So in other words, we are multiplying or dividing kind of, but I just want to think about multiplying by a constant ratio each time to go from one term to the next. So here in example 1, if that's the case, determine which sequences are geometric. So if we're looking for the pattern to be multiplication, then we should be multiplying 3 by something to get 6. So we can reverse that by dividing 6 by 3 and seeing that would be 2. So if this is a geometric sequence, we're going to multiply 3 by 2 to get 6. Then we're going to go from 9 to 6. Well, if we divide 9 by 6, we'd get 1.5. So we can actually stop right here if we wanted, because that is not the pattern here. We are not multiplying by a constant ratio each time. You might notice we're actually adding 3 each time. So this is arithmetic and not geometric, because there is a common difference. The pattern is adding. So let's move on to our next one. 3 times 2 negative 6 to 12 to negative 24. So again, if we want to know what we're multiplying by to go from 3 to negative 6, we divide, and it's negative 2. To go from negative 6 to 12, we can divide, and that's negative 2 again. And you need to do this, of course, at least twice. Go ahead and maybe do it a third time just to make sure. But the pattern is multiplying by negative 2 here. So 3 times negative 2 is negative 6, times negative 2 is 12, times negative 2 is negative 24. So yes, this is geometric. And we know that because there is a constant ratio multiplying by negative 2. And then our last sequence. So this one, if we're multiplying 6 by something to get 2, we're doing 2 divided by 6, which is 0.3 repeating, which you may realize is 1/3. Then we're going from 2/3 to 2. So, from 2 to 2/3, so we're going to divide 2/3 by 2, and that gives me 1/3. And if you keep following this pattern, you may also notice, so you're multiplying fractions straight across. 2 times 1 is 2, 3 times 3 is 9. So that would continue this. So again, yes, this is geometric, because we have a ratio of 1/3. So let's continue. Example 2, find the next term in the geometric sequence. So if we know this is geometric, we know we are multiplying. So we're going to try to work through there. Multiplication, 324 times something to get 108. So we reverse it, 108 divided by 324. We get that 0.3 repeating again. So my ratio is 1/3. We've already got 4 terms, so I want the 5th term in the sequence. It is going to be 1/3 of the 4th term, which is 1/3 of 12, and I know that to be 4. So the next term in this sequence would be 4. Just like in arithmetic sequences, it can be nice to have an explicit formula for the geometric sequence so that we can find any term that we want. So that it has the same reasoning as the arithmetic sequence formula. We have a sub n equals a sub 1 times r to the n minus 1 power. And that's where a sub 1 is the first term, r is the constant ratio we're multiplying by between the terms, and n is the desired term number. So like if we want the 10th term, n would be 10. So we're going to do one more example in this video and then have another video coming up later. Suppose a bouncy ball is engineered to bounce up to 95% of the height of the previous bounce. If the ball is dropped and the first bounce is 100 centimeters, about how high will the 25th bounce be? So we drop a ball and it comes up to be 100 centimeters on the first time we bounce it. And we want to know the height of the 25th bounce if it comes up 95% of the previous height. So we can kind of follow along and remember 100, if we want to find 95% of something, we're multiplying by 0.95. So the next bounce would come up to be 95 centimeters, so very close still. And we could keep going, keep going, keep going. But I want to use this formula because that's going to be faster than doing this 25 times. So we're going to use a sub n equals a sub 1 times r to the n minus 1 power. We're looking for the 25th term, so that's a sub 25. A sub 1 is the first term, that's the first bounce, so that was 100 centimeters. The constant ratio is 95%, 0.95 or 0.95, and we need to raise that to the 25 minus 1 power. And that's because if we need the 25th bounce, we would be multiplying by 95% 24 times. The same logic as we did with the earlier arithmetic sequences. So 100 times 0.95 to the 25 minus 1 power is about 29.199 centimeters. So I'm definitely not just going to call this 29 centimeters because that implies at least a little bit that it might be an exact number. I want to show that it's not 29, so we're not going to be able to write an exact answer in some cases, or it wouldn't be very helpful anyway, but I'll go out to 3 decimal places, and this time that 9 rounds this 8 up, so 29.199 centimeters.